it's 5 p.m. And I think there may be more people joining, but I think it's time to start my talk. And for the audience, can you hear me?
Yes, I can hear.
Okay, thank you, thank you. Okay, let me share my screen. Okay, hello everyone. Thanks for coming to my today's talk. I'm Xiaozhou Feng from the Ohio State University. And today I want to talk about my recent work about the measurement-induced phase transitions on the dynamical quantum trees. Okay, and this work is done by 3 people. It's by me and my advisor, Professor Skinner, and my collaborator, Professor Adam Nahum from the ENS Paris. And I want to mention that this paper has been posted on arXiv, and for the interested audience, if you want to read more details, please take a look at our paper. Okay, in this talk, I will talk about the measurement-induced phase transitions. We know that in the usual condensed matter physics, we care about different kinds of phase transitions. For instance, like this picture, the mean field for magnetic transition of the magnetization. Usually, we will consider some thermal equilibrium state or some ground state. And we will have some parameter to tune, which can be either the temperature or some parameters in our Hamiltonian. And usually, we will be able to characterize this phase transition by the expectation value of some observables, such as the magnetization in this plot. However, on the other hand, recently people find a different kind of phase transition, which doesn't satisfy these properties I have mentioned before. Okay, people have done a lot of excellent work in this field. So for review papers, please, you can take a look at these 2 papers to get more details. Basically, people find that this kind of phase transition describes the dynamics of the quantum body systems. The more important thing is that we can no longer use the expectation value of some operator to characterize this phase transition. We have to use some quantity like the entropy, for example. If we take a look at this picture, suppose we have some quantity which can be the entanglement entropy, for instance, and we have some parameter p to tune. Then, if we increase p from 0 to 1, here p can be some random measurement rate, for example. We will see a phase where the saturated value of this entropy exhibits some volume law, and in the second phase, we will see some area law. Okay, I will talk about these pictures with more details later. So if you do not understand this picture well, it's fine. Okay, now let me review some very background knowledge for you. Let's consider a 2-spin system. We can write down some product state like this, but we can also write down some entangled state. I will call it psi 1. Okay, if you try to calculate the entanglement entropy, which I will explain later, you will get non-zero value for the second state psi 1. So this gave us some intuition about the entanglement. We can think it to be some information shared by not some subsystem alone, but the whole system together. And we can also consider the measurements. So suppose we still consider this 2-spin system. And now I try to apply the measurement on the first qubit and along the z direction. And for the product state, after the measurement, I still get the same result. On the other hand, for the entangled state, after the measurement, we will have 2 possibilities. So one thing interesting we see is that our measurement on the system A, which is the first spin, will influence the final state on the system B, which is the second spin. And another thing we can see from this result is that the measurement will turn an entangled state into a product state. So our process 1 becomes a product state after measurement. So in this way, we can think that the measurement will try to destroy the entanglement, and we will use this naive picture later. Okay, now we can talk about the measurement-induced phase transitions. Okay, roughly speaking, I can think this phase transition to be a kind of phase transition characterized by the dynamics of quantum entanglement. If I consider this well-studied example of the quantum circuit, which is a 1D qubit chain with a product state at the beginning, and I turn on some random unity time evolution, which means that in this picture, each green block represents some two-body unitary operator. Then I can ask the question, okay, suppose I separate the system to be two parts by this red dashed line, and I want to ask, okay, how does the entanglement between the two parts change with time? To answer this question, I need to introduce the concept of entanglement entropy. Suppose I consider the whole density matrix of the system, and I trace out the system B, for instance. Then the partially trace density matrix, I will call it rho A, and I can define the entanglement entropy using rho A. And then I can ask, how does the entanglement entropy between the two subsystems evolve with time? Okay, then people find that, well, the entanglement entropy will increase with time, and finally it will reach to a saturated value, which is proportional to the system size. So we call it the volume law. And now I want to ask, okay, what will happen if I add the measurements into the system? If we still look at the picture, now I have some measurements represented by the green circle. Here, the arrow represents my measurement outcome. And I will randomly apply these measurements based on some measurement rate P. If I still separate the system to be two parts, the left and the right, okay, now I still want to ask this question. How does the entanglement between the two subsystems evolve with time? Okay, this problem has been solved in previous work, and the early work about this problem is basically these three papers. So for interested audience, please take a look at these papers for more details. And basically people find that when the measurement rate is quite small, in general, we should expect that this is close to the case with zero measurement rate. And we did have the volume law, so the saturated value of the entanglement entropy is still proportional to the system size. On the other hand, when the measurement rate is not enough, people find that the saturated value of the entanglement entropy is an order 1 parameter, which is independent of the system size. So it is called area law. And there will be a critical point which separates these two phases, and it will be called it will exhibit some algorithm behavior of this entanglement entropy. Okay, then we can see that by tuning the measurement rate, the growth of the entanglement will exhibit different scaling behaviors. In this case, we will get some phase transition, and we will call it the measurement-induced phase transition. Okay, then people may ask, why should I get a phase transition? To get some intuition, let's recall some knowledge we have discussed before. The first thing is that we know that if we have some unitary time evolution, it will try to increase the entanglement between the two subsystems. On the other hand, we know that if we consider the measurement, it will try to cancel the entanglement between the measured qubit and the rest of this system. Well, using these two naive intuition, we can think that there will be a competition between the unitary time evolution and measurements. In this case, we should expect some phase transition. And if we focus on the zeroth order re-entropy, and people find that this problem can be exactly mapped to the proclamation problem. So this phase transition can be described by the proclamation phase transition. But I want to apologize that I will not talk about the proclamation problem with details here. It is not directly related to my topic. So for interested people, please read this paper for more details. Okay, although we already have some understanding about the phase transition, we still have many challenges. The first thing is that, well, it's in general very difficult to study the phase transition analytically. Okay, before we have seen that we have the exact proclamation solution, but it's only true for the classical creative point. For other order of entropy, it's in general that the quantum creative point is smaller than the classical one. In this case, it means that we will have some entangled phase, but we will have some intermediate regime where we have the p larger than the classical, smaller than the quantum classical creative point, but we all have already entered the disentangled phase. And so far, we have no analytical understanding about the quantum creative point and the creative exponents near the critical point. The second challenge is that, well, it is in general very hard to simulate for large system size. People already developed some techniques called Clifford circuits, where we consider some limited set of gates, and which makes the problem simulable on some classical quantum computer. So the system size can be 5 to 1,000 qubits. However, if we want to consider a broader set of gates, such as the hard random circuit, then usually the system size will be roughly 20 qubits. In this sense, it is in general very hard to get accurate enough result about the critical point and the critical exponents. The third problem is that it is in general very hard to observe in experiment. Well, as I have said before, we can use no operator's expectation value to see this phase transition. So we need to consider the density matrix of the system. To get the density matrix, we need to use the quantum tomography technique, which requires exponential number of detections for the same density matrix. And an even worse problem is the post-selection problem. Since we need to get the identical copy of the density matrix. However, remember that we will have random measurements in the dynamics, which means that to get the exactly identical copy of the density matrix, we have to have the exact same set of measurement outcome. This means that even get only one identical copy of the desired density matrix, we need to run an exponential number of realizations to pick the one with exactly same set of measurement outcomes. This makes the phase even harder to be observed in experiment. Okay, so far we already have some experiments about this phase transition. We have some results on the superconducting qubits, and we have some results on the trapped ions. However, this problem is in general very hard to solve. So I want to talk some model in this talk which can only solve all these three problems. Okay, before talking about our model, I want to mention one more very important thing, the purification phase transition. If we going back to this picture, if we start with the product state, there will be a phase we have the non-zero entanglement entropy, and we will also have a disentangled phase. However, if we consider a maximum mixed state at the beginning instead, then there will be a phase that the initially mixed state is not purified, and there is a different phase, the initially mixed state is purified. And this critical point is exactly that in the previous case. This work is done by Gullens and Hughes in 2020. Sometimes this purification problem is easier to study. So it gives us an equivalent method to study this phase transition. And I will use this purification phase transition in our work. Okay, now let's talk about our model. Basically, we propose some quantum tree model. What is a quantum tree model? You can think that we have some tree-like tensor network. So as I have said before, I want to consider the purification process. So we will have a maximum missed initial state at the beginning. And I will keep discarding some qubits, and the remaining qubits, the word lines of them will form a tree-like structure as the picture on the left. At the end, we will only have one qubit on the top. I will be interested in the final state of this root qubit. Is it a mixed state or is it a pure state? Okay, I need to mention that although I use the name leaves and root, in fact, our time direction goes from the bottom to the top. So don't get confused about the names. Then, if we take a look at the phase diagram, we can have some parameter to tune, which can be some measurement rate or the measurement strength. Then we will have a phase that the root qubit of the tree is still a missed state, it's not purified. But we will have a different phase that the root qubit of the tree will become purified by keep increasing the system size. There are some advantages about considering the quantum tree model. The first advantage is that we can exactly solve the critical point and critical exponents analytically by mapping to some statistical polymer problems. The second advantage is that the numerical calculation can be done very efficiently by a so-called pool method, which allows us to go to a very large system size. Okay, I need to mention that the quantum tree model has already been studied in early work, and you can take a look at this paper for more details. However, in this model, they can only solve the first measurement case, which I will explain later, and they do not have a well-defined time order. So they do not find a solution with zero measurements. I want to solve this problem. So then I want to mention what is the first measurement and what is the real measurement. For the real measurements, it is just the real measurements in physics. We will have the random measurement outcomes, and the probabilities will be based on the Born rule. However, on the other hand, the first measurement, the measurement outcome will be predetermined. We have no randomness of the measurement outcome. Then you may ask how to get the first measurement. To get it, let's think about the following protocol. Let's run the system with just real measurements for multiple times, and then we will discard the realizations with the wrong measurement outcomes. We will only leave the realizations with the desired measurement outcome set. In this way, we will get the first measurement. Okay, now we can talk about our quantum tree model. Basically, we propose a quantum tree model which has the well-defined time order, and it can work for both the first measurement and real measurement case. This is a cartoon about our tree model. Okay, I will call it collapse process because we will keep discarding the qubits. I will also mention the expansion process later. Again, I will consider the initial state to be a maximally missed state, and I will allow some projective measurements which will discard half of the qubits on each discrete time. And for this node T, it is in general a tensor. It will contain all the details about our tree model. It can have some unitary matrix. It can have some weak measurements. I will consider the final state of the root qubit, the purity of this final state. I need to mention that in our model, we have no randomness about the locations of the measurements. This is different from the quantum circuit case we have discussed before. Okay, this plot talks about the details about our tree model. For the red block, it represents a weak measurement with strength theta. So to think about the weak measurement, you can think that we will try to entangle the system qubit with an ancilla qubit for a short time. After that, we will try to measure the ancilla qubit, and this will give some influence on the system qubit. So we will call it this process weak measurements. In general, the weak measurements can be described by the cross operator. We will have some parameter theta. We will call it the measurement strength. And the subscript sigma will represent the measurement outcome. We will, in general, allow some random basis, which is represented by the hard random unitary matrix U. In general, the cross operator will satisfy this normalization relation. After acting the weak measurements, our density matrix will transform in the following way. And our theta will goes from pi/4 to pi/2. When theta equals pi/4, it means that there is no measurement at all. It just behaves like identity operator. So our maximally mixed state will always stay maximally mixed. On the other hand, if theta becomes pi/2, then the weak measurements, they just behave like the projective measurements. So our tree model will become purified at the very first step. And for the blue block, it represents some hard random two-body unitary matrix. For the red bar, it represents some projective measurements, which can be either real or forced. Then, if we consider this node in the previous cartoon, it in fact represents this orange block in the left picture. So we are interested in the purity of the top qubit. We are interested in the dynamics of this state by keep increasing the system size. We found that our model will exhibit a transition from a non-purified phase to a purified phase by tuning the weak measurement strength from pi/4 to pi/2. So in general, our result can be shown in this picture. So for the entropy S, we found that it will continuously decay to 0 by keep increasing the weak measurement strength. For pi/4, as I have said before, we will have weaker measurements, but when theta close to pi/2, we can think that we will have stronger and stronger measurements. I need to emphasize that here this S is not the entanglement entropy I mentioned before. It is just the Euro entropy defined by the density matrix of the final qubit of our tree model. Here, MPT means that we have only real measurements in the tree model. And for FMPT, it represents we only have forced measurements in our tree model. And one thing we found is that the critical point of the real measurement case is smaller than that of the forced measurement case. And we will see this phenomenon later. Okay, as I mentioned, we in general allow some hard random basis, which ensures that we can only keep the eigenvalues of the density matrix. Since we just consider a 2x2 density matrix, the normalization relation allows us to only consider the smaller eigenvalue. We will call it Z, and it goes from 0 to 1/2. It will have all the interesting properties about our tree model. When Z is equal to 0, we will have a pure state. When Z equals 1/2, we will have a maximally mixed state. To get a statistical behavior, we want to consider a quantity called Z typical. It is defined by considering the average of log Z. The reason to consider log Z is because the probability distribution of Z is a very sharp peak. If we just consider the average of Z instead, it just tells us the information about the peak of this probability distribution. If we consider log Z instead, we will have a smoother probability distribution. Then it will encode more information about the whole probability distribution. For the forced measurement case, our numerical result is shown in this picture. And the y-axis is log Z typical, and the k represents the system size. And when the color is closer to purple, we will have weaker measurement. When the color is closer to yellow, we will have stronger measurements. So we see that by tuning the measurement strength from pi/4 to pi/2, we see two phases. In the first phases, the typical value becomes saturated even with the system size goes to infinity. On the other hand, the typical value will keep decaying to 0 by keeping increasing the system size in the other phase. And the critical point is shown by the red dashed line. And for the real measurement case, we have similar behavior. We still have a phase where the typical value becomes saturated for even infinite system size. And in the second phase, the typical will keep decaying to 0 by increasing the system size k. The difference is that the critical point for the real measurement case is smaller than that of the first measurement case. This is consistent with our entropy plot we discussed before. Okay, now let's talk about how to solve our tree model. Basically, for the quantum tree model, we can use some recursion relation to study it. What does it really mean? If we consider the whole tree model, we can regard it as two subtrees acting on a node. As I have said, we do not need to keep the basis of the density matrices. We just need to know the z-values of these two subtrees. Then the z-value of the whole tree is in general a function of the z-value of the subtrees and the t-tensor, which describes the details inside this node, and S, which represents the set of measurement outcomes inside this node. And we can write the density matrix of the two subtrees in diagonal form. And we can obtain this t-tensor by considering the details of the node. We found that it can be written as a tensor product of the two-body unitary matrix and the cross operators. Here, this sigma 1 represents the measurement outcome of the first weak measurements. Sigma 2 represents the measurement outcome of the second weak measurements. Sigma 2 prime represents the measurement outcome of these projective measurements. Using this t-tensor, we can obtain the density matrix of the whole quantum tree. It is written in this form. And for a specific measurement site inside this node, the probability for that site can be obtained from the t-tensor. Okay, now let's see how to solve this recursion relation. As I have said before, we will have a non-purifying phase and purifying phase. The good thing about the purifying phase is that the typical will decay to 0 by keep increasing the system size, which means that it can be as small as possible. In this sense, we do not need to keep the full recursion relation. We are allowed to keep only the leading order of the recursion relation. And for the first measurement, one more thing is that the measurement outcome is predetermined. Here, I will assume them ought to be up. This simplifies our calculation. Then we can write down the recursion relation in this form. Here, the coefficient A1 and A2 can be obtained from the t-tensor, and we will ignore higher order corrections about z. Using this linearized recursion relation, we can solve the purifying phase. And to study it, we define some generation function g in this way. Well, you can think this parameter x as position, and you can think this discrete number k as some discrete time. Then this function g can be understood as a moving wave to the left with the wavefront exactly located at log z typical. In this way, the recursion relation can be regarded as the discrete version of the Fisher KPB equation. And this has already been studied in early work about statistical polymer problems. And we will use their results. One thing important about the Fisher KPB equation is that in general, we will have a family of solutions. However, for the physical one, it is the minimal velocity. So the velocity of the wavefront will have a parameter lambda, which labels different members of the solution. But we will only keep the lambda, which gives us the minimal velocity. And if we consider the critical point, it will give us 0 ballistical velocity. then V equals 0 at the critical point. Using these two properties, we are allowed to solve the critical point. It turns out that the critical point satisfies the following equation. Solving this equation, we find that the critical point is 1.4201. And if we compare with our numerical calculation, we find that we have good match between this result and our numerical calculation. Besides the critical point, we are also allowed to study the scaling behaviors near the critical point. For instance, we can consider the saturated value of the typical when k goes to infinity. We find that when theta is close to the critical point but stays in the non-purifying phase, then log the typical will exhibit the behavior of 1/square root of delta theta. This coefficient C can be analytically calculated, which is shown by the red dashed line. And we see that it is consistent with our numerical result represented by the blue dots. And we can also consider the behavior when we're exciting a case at the critical point. As I have mentioned before, we will have 0 ballistic velocity at the critical point. However, we are still allowed to have some sub-ballistic behavior. And our analysis shows that the typical will exhibit some k to the 1/3 behavior at the critical point, and which is shown by the red dashed line, and it is consistent with our numerical calculation by the blue dots. Okay, before we talk about the forced measurement case, now I want to talk about the real measurement case. The big difference for the real measurement case is that here we can no longer ignore the measurement probabilities for different outcomes. However, the good thing is that if we stay in the purifying phase, we can still ignore the higher order correction of Z. Then it turns out that the probability distribution will be independent of the Z value. It will only be a function of the T tensor and the measurement outcome site. Then in the purifying phase, we can write a modified linearized recursion relation in the following way. It gives us a different velocity, but in general, we can still consider the lambda which gives us a minimal velocity, and at the critical point, V still equals 0. Using these two properties, again, we find an equation for the critical point. By solving this equation, we find that the critical point is 1.1001, and we find that it consistent well with our numerical calculation. Okay, after talking about a critical point, we can again talk about the scaling behavior near the critical point. We still find that for the typical, the saturated value in the non-purified phase exhibits the similar 1/square root of delta theta behavior, which is shown by the red dashed line, and it is consistent with our numerical calculation. For the critical scaling behavior at the critical point, we still have this k to the 1/3 behavior, and it is checked by our numerical calculation as the blue dots. Okay, now let's compare the forced measurement quantum tree and the real measurement quantum tree. The first difference is that they have different critical points. The real measurement case will have smaller critical point compared to the forced measurement case, but they exhibit similar scaling exponents I have said before. Okay, they also have some other small differences, but I will not talk about that in this talk. Okay, so far we have talked about our tree model, and we found that it can be solved analytically, and we can get both critical points and the critical exponent. Now I want to propose some experimental protocol which can avoid the post-selection problem. To explain the experimental protocol, we need to introduce a so-called expansion process. Here is a cartoon of our expansion process. For the initial state, we will consider still the maximum mid state. However, in this case, we only have a mixed single qubit state. And our system will keep interact with some qubits in the environment. All these later get involved qubits, I will assume them to be stay up. Then later we will have many qubits at the final time. So you can think this expansion process to be the inverse of the collapse process. And we found that this expansion process can be exactly solved by considering the collapse process with a maximum mean state at the top. We will be interested in the final state of the system. Will the final state be a mean state or it is a pure state? And we will expect that the system will exhibit a similar phase transition as the collapse tree. Okay, for our experimental protocol, we have something a little different. Here, we introduce one more acyclic qubit. And at the beginning, we will prepare a J state between the single system qubit and this acyclic qubit. Then, at a later time, if we want to consider the density matrix of the system, we can just trace out the reference qubit. Here, the capital T represents the tensor of this whole expression tree. Then we find that it just gave us the density matrix of the expansion process we have discussed before. One thing important about our protocol is that for the final state of the system and the acyclic qubit together, it is still a pure state. It means that to consider the purity of the system, we just need to consider the density matrix of this reference qubit alone. In this way, we'll avoid the quantum tomography problem of this large system. Okay, now I want to mention our protocols. The first step is we will prepare the GHZ state between the single system qubit and this reference qubit, as I have said. Then I will construct the tree with random unitary matrices and measurements. After knowing the record of measurements, we will be able to kinetically calculate the density matrix of this reference qubit using this measurement record. It will in general give us the following form. Here, the vector n will be related to the z value of our system. Okay, then we can apply a measurement for the reference qubit along the direction n, and we will have measurement outcome which can be either +1 or -1. We will just record this measurement outcomes. And then we will repeat the above procedure many times. Okay, to see why we should see the phase transition in this way, we can get some intuition by the following argument. We will have in general two phases. We will have a non-purified phase where we have a mixed final state, but we will also have a purified phase where we will expect some pure state. For the purifying phase, since we have pure state, we should have very high accuracy about our predictions about this measurement outcome tau. On the other hand, for the non-purifying phase, since we have a mixed state, we will have a very low accuracy about our prediction. Then, by checking our prediction accuracy, we will be able to see this phase transition. And we can calculate our experimental calculation about this average z value using the record of the tau, and it should be consistent with the theoretical predicted average z value. So in this way, we will be able to see the phase transition. You can notice that in the above protocols, we do not need to get some identical copies of a density matrix. In this sense, we avoid the post-selection problem. Okay, now let me give a summary about my talk. First, we propose a quantum tree model which exhibits the measurement-induced phase transition for both the first and real measurement case. Second, we found that the phase transition can be exactly solved, and we derive a solution for the critical points and critical exponents. At the end, I propose an experimental protocol which we will be able to see the phase transition, and we can avoid the post-selection problem. Okay, as I said before, this paper has been posted on arXiv. So for the interested audience, please read the paper for more details. Thank you. Okay.
Can I ask a question?
Okay.
Yeah,
Yes.
this is Matthew Fisher. Really nice talk.
Okay, thank you.
So the last part, you have a classical calculation you have to do, I guess. Is that right?
Yes, yes.
And how does that scale with the number of qubits, the time it takes to do the classical calculation?
Okay, yeah, this is a very good question. So for basically the classical calculation, it can be done very efficiently. I think the time scale will be just proportional to the layers of K, of the tree K. So the time scale is just the linear order of K. But we need to mention that here the K is not the total number of qubits. It is the total layers of the qubits. So in fact, the actual number of total qubits will be 2 to the K. Is this solve your question?
Yeah, so it's really efficient. Yeah, thanks.
Thank you. Any other questions?
Question from Xiaozhou.
Okay, okay. Hi, Tian.
Hi. So I want to ask this expansion experimental protocol. So
Yes.
is it from this figure, is it just the inverted figure of collapse process that all the calculations are similar? For example, if you have this W in this protocol that corresponds to the cross operator in your collapsing protocol, and then this upstate is just a forced measurement.
Oh yeah, thank you, Tian. This in fact it is a very good question.
Okay.
Yes, we can consider the expansion tree as the collapse, the inversion case of the collapse tree. But one thing special is that, okay, if you look at this cartoon, you will find that all these later get involved qubits, I will assume they ought to be up. So yeah. If you consider the collapse process, this violates the case of the projective measurements. So the tricky thing is that even in this expansion case, even if we have only real measurements inside each node,
yeah,
for the expansion to analytically calculate for the collapse process, we have to consider a mixture case, which means that we have both real measurements and forced measurements. And I haven't discussed this mixture tree in my previous talk. Before, all my talks they only focused on the completely real or completely forced measurement trees. The mixture tree, our calculation turns out that it will be more complicated. And okay, I want to mention that based on some of my recent calculation, it seems that the mixture tree can still be calculated using some recursion relation. But just in general, we should expect that the mixture tree case is more complicated than the real or forced measurement tree. Does this answer your question?
Yeah, so I wanted to confirm that by supplementing this upstream in the expansion process, you are not getting the forced measurement in the collapsing tree, but you're getting a mixed
we have a mixture tree.
Measurement.
We have the real measurements inside the node, but we will have forced measurement for this area. So if we we're going back to this picture, we will have real measurements inside the node, but for this projective measurements, they will all need to be assumed to be forced.
So if you were to perform the experiment, you will get the exponents from the forced measurement result. Is that correct?
I think it should be correspond to the mixture tree case. So
okay.
So I think some future work is still needed to check whether we can still get the same critical exponent.
Okay. Okay.
Thank you.
Okay, thank you. Thank you.
And any other questions?
Hi, thank you for the nice talk. I had a brief question, just a clarification. So, are you doing the measurement at every step of the tree?
Oh, you mean the Tibetan tree or the collapse tree? Okay.
This tree for the experimental protocol. Are you measuring it every layer? Yeah.
Yeah. I think for every step we need to do the measurement inside the node. So if you look at this picture, here this up qubit is some input, so we do not need to do some measurement. We just prepare this up state. But for these two weak measurements, we need to do them for every node inside these trees.
I see. Okay. Thank you.
Thank you. Other questions?
I can ask another one.
Yeah, please.
So I'd like to know if there's any intuitive picture why the real measurement is more destructive. It means that with a smaller measurement rate, you can get the purifying phase.
Oh, yeah, this is also a very good question. A simple intuition about this is that, okay, if we just consider a single qubit state, for instance, for the real measurement, it will try to have a higher probability to turn this state to. Okay, so sorry. Let me organize my words. Sorry.
Yeah, no problem. Take your time.
Okay. Okay. So if you just consider a single qubit state, for instance, if we consider the real measurement case, then in general we should expect different probabilities for the up and down.
Yes.
So suppose we have higher probability for the up, right? Then after the measurement, we will have higher preference to be up. So if we consider the statistical average, we will have a higher probability for up. But for the first measurement case, we will have equal probability for up or down. This just depends on which state you predetermine. In this sense, the real measurement, it will give a higher preference to. It will give the tree model a higher preference to be purified compared to the first measurement. Yeah, this is a very naive picture about why the real measurement case will have can be purified with smaller measurement strength.
Okay. So I guess it has to do with the tree structure from your argument.
Xiaozhou, do you mind if I say this a slightly different way? What you said is correct.
Yeah.
Do you mind? Sorry.
Okay.
So
Go
if you
ahead,
think about a single spin, a pure state lives somewhere on the surface of a block sphere, and a mixed state lives somewhere inside the block sphere.
Oh, that's right. Yeah.
When you make a weak measurement, you move the state of the spin somewhere closer to one of the poles of the block sphere. Like you're averaging, doing nothing with a strong measurement that would move it all the way to the North Pole or the South Pole. So if you make a measurement in the North Pole direction, you move the state of your spin from slightly closer to the North Pole of the block sphere. When you do forced measurement, it's almost like you move your spin toward a particular direction, regardless of where it is currently. Move it
Yeah.
always closer to the North Pole, regardless of whether the state of your spin currently resides in the north half of the Bloch sphere or the south half. Always move it toward the North Pole. If you do a real measurement, then you say, pick the state of the spin, pick whichever pole it's closer to and move it closer in that direction.
Oh, I
Like
see.
you're preferentially moving toward the pole that it's already closer to. And so in that sense, it tends to be more purifying.
I see. I see.
Yeah, that's right. Thank you, Brian.
No, sorry to take your question away from you.
Other questions? Okay, I guess we do not have any more questions. If there are no questions, I will end this talk soon. And again, thank you guys for coming to my talk. And for interested audience, please take a look at our paper on arXiv for more details. Thank you, guys.
Thank you.
Yeah, thank you, Xiaozhou. Well done.
Thank you.
Thank you.
Thank you. Very good talk.